I don't know why it does that.
Getting ready to know the truth.
Yeah.
Didn't like the day card.
That's it. It's like one of my teenage kids. I should say former teenage. So, when is momentum conserved, when is it not? This is when we get into open system and closed system. In a closed system, my initial momentum equals my final momentum. In an open system, the momentum is going to change, and that's basically the impulse. Coming up with a mildly informal definition that in a closed system, you're taking into account all the objects involved. In an open system, you're looking at, there are some outside influences, external forces, generally as it's preferred. So when I had these two things colliding, it was just these two things. There was nothing else involved in the problem, so my momentum was conserved because I had two objects here and I took both of them into account. But when I did my impulse over here, I ignored that and looked at just this one. And so there was a change in momentum because I ignored this outside influence. So open system, there exists, that's what the backwards E means, there exist external influences. All objects are considered. All objects influencing each other, I guess I should say. So in the case of my dropping the marker, what object was I ignoring? Because we talked about that the marker had a change in momentum, therefore it had to be an open system, therefore there had to be some object outside of it that was causing an influence. What influenced the marker to change its momentum?
It's weight.
What caused the weight?
Gravitational force.
From?
Gravity.
You're all dancing around, you were so close. What causes the weight of the marker?
Force due to gravity.
From? I feel like we've been here before. Forces are caused by objects. What object is causing that force due to gravity?
The pull there.
The Earth. The Earth is the other object. This was an open system because I ignored the Earth. Just saying it has weight is still, unless I bring in what is happening to the Earth, it's still ignoring it. So if I want to make it a closed system, so my total momentum stays zero, I drop this, I can see how this changes, and then I also see how the Earth changes. So as this fell, the Earth came up. For all of you felt it. Just in case again, get ready to feel it.
Ooh.
And I got on camera that I couldn't catch. But you felt the Earth sort of jerk upwards?
Oh, yeah.
Now, if I jump off the table, I've done the calculation before, if I jump off the table, the Earth comes rushing up towards me, and it comes up about the size of a nucleus of an atom. So the order of femtometers. And it's one of those things, you're just, trust me, the Earth moved. I'm not even sure we have any instruments that would measure how much the Earth moved as the marker fell. Because there's quite possibly someone on the other side of the world dropping a marker at the same time, in which case we now have another object influence, and the Earth is basically staying still. And yes, I know not exactly the other side of the world, because that's in the middle of the Pacific Ocean. All right. The preliminary stuff. At this point, I hope you know the formula for momentum. The fact that you recognize that it is a vector, and so direction matters. And that in a closed system, the total momentum beforehand equals the total afterwards. That is what I'm hoping. And the second hope is that in your mind you're going, of course, we got this. So let's do the same problem 3 different ways. And I'm going to gamble on the fact that we're going to get the same answer every time. Round. I think we'll make it 10 meters, whether we did that one way before or not. So first off, chapter 2. So I have some displacement, initial velocity, final velocity, acceleration, and time. What do I know?
You know the displacement is 10 meters.
What assumption did you just make?
That the ground is 0.
Down is positive.
That's the assumption you made. Well, the fact that you're making ground 0, that's when we do the chapter 7 way of doing it. All right, so displacement's 10 meters. What else do we know? We know 2 other things.
Acceleration is 9.8 meters per second squared.
What assumption did you just make?
That we're on Earth.
Okay. All right. And one more piece of information.
Initial velocity is 0.
Yep. What's the key word?
It dropped.
Yep. All right. So we now have a constant acceleration. We have the cake formulas. So it looks like VF squared equals VI squared plus 2A dot delta S. And so we have VF equals the square root of 2 times 9.8 times 10. Which is 14.1-ish? No, 14.8. Let's finish it off.
Meters per second.
All right. So using the chapter 2 knowledge, we figured out that it's going 14 meters per second when it's fallen 10 meters. Oh, I'm going to throw chapter 4 into it. Chapter 4 is not going to tell us how fast it's going at the end. It will tell us the acceleration. So we did the force diagram. We have a force, its weight acting down. I know F equals MA. I have one dimension here, so I have weight is equal to MA. Mg equals MA. Equals G. So the chapter 4 stuff would just tell us what the acceleration is. Chapter 7, energy. We needed to look at forces anyway. What can you tell me about the force acting on it, besides that it's weight?
It's pulling it down.
The weight is slowing it down?
Pulling.
Pulling it down, okay. Thank you, that's so much better than the first, what I first heard. Yes, that is true. Let me rephrase it. Is this a conservative or non-conservative force?
Conservative?
Like you mean it.
Conservative.
Yes, absolutely. Gravitational force is conservative. So therefore, my energy is conserved, because I have no non-conservative work. Energy initial equals energy final. K initial plus U initial equals K final plus U final. Get ready, you know it's coming. What's the formula for kinetic energy?
1/2
V squared.
What's the formula for potential energy?
Which one?
Thank you. The one associated with weight. We've dealt with 3 potential energy formulas. That's the one. The hint is that since weight is equal to mg, just checking on 8. So mgh initial equals 1/2 mv final squared plus mgh final. What can we get rid of? Or what's equal to 0?
Can we get rid of height?
We have 2 heights. Get rid of both of them.
Final one?
Final height. Why?
Because we can.
Okay.
You go.
Because Amy says so. She just established by making that statement there that h is equal to 0 here. Despite the fact that Kino wanted the ground to be 0. Amy said, not today, not in my house. I apologize, I mispronounced your name. It's Kino, not Kino.
Oh, no, you're fine.
I'd like to think that's the only time I've done that, but,
It is.
oh. All right. What else can we get rid of?
Initial velocity.
Because the initial speed is 0. And we can now get rid of one more thing. We can't get rid of a term, but we can get rid of a factor.
Yeah.
Yep. And so what I'm left with is GHI is equal to 1/2 VF squared. And so my final speed is the square root of 2 times G times H sub I. The height based upon where we have 0. And I'm thinking that's somewhere around 14. And then the chapter 8 version. Questions about what we've done so far before we do the momentum bit? All right. I'm gonna treat this as an open system, because I really don't want to worry about the Earth moving. I'm just gonna make the assumption, the bold assumption, that the Earth is not gonna move significantly while this rock falls 5 meters. So therefore, my impulse is equal to the change in momentum, and impulse is also the force times time. Now, using momentum ideas here is not the most convenient, because we're basically gonna do a lot more work than we ordinarily would. But the example I do after this is gonna show where momentum actually does have some conveniences. So this is P final minus P initial is equal to the force, basically weight times time. This is mass times Vf minus mass times Vi is equal to mg times time. Now I dropped the vector symbol on the right hand side. We already established down as positive. I assume we're going to keep that. And so this is just in the positive direction. Emphasize that. I'll just put a plus sign right there just to emphasize the fact that it's downwards. What can I get rid of?
Initial velocity.
What else can I get rid of?
Mass.
Yeah, mass. So my final velocity is positive GT. So we just need to know how much time it takes to fall, to go that distance. This is why it's not particularly convenient, because we're basically doing what we have right here. Delta S equals VIT plus 1/2 AT squared. Conveniently, this term drops out. And what we're left with is time is equal to the square root of 2 times delta S divided by A, or actually G specifically, which is square root of 2 times 10 over 9.8. And so this is 9.8 times that square root times 20 over 9.8, which will end up being the square root of 196, which is 14. It is positive, so therefore it is in the positive direction, which is down. Did I make a mistake, Greg? Okay. And it's natural that it all works together because it's all based on Newton's second and third law of motion. It's just disguised. Questions at the moment? All right, let's take a 5-minute break, come back, we'll do some, when is it, can you tell what I should be using momentum, Newton's laws, or energy, and then we'll get into collisions. I'm gonna pause this, and it'd be appreciated if someone would remind me when we start up again that it's paused. All right, so let's take a look at this situation right here. We have a car that's cruising along at 30 meters per second. The driver slams on the brakes and the wheels lock, and they stay locked for 2.5 seconds. Then he takes his foot off the brake. Maintaining a constant velocity again, not 30 meters per second anymore, and then slams on the brake again at this point and skids for 20 meters. And so the question is, how fast is he going at this point right here? Or if he stops, at what point does he stop? I have three things at my disposal. I have Newton's second law. I have conservation of momentum and conservation of energy. Because of where we are in the textbook, let's just narrow it down to energy and momentum. Said conservation, it's actually not conserved here. So at this point, when I'm going from here to here, shall I consider momentum or energy? Which is the one that's going to be most convenient? Why? This feels right? Yeah.
Because it's a vector, and we're looking for the specific direction,
So we'll never use energy?
not necessarily.
The fact that since the vehicles are only gonna go in one direction, the vector aspect is not the key piece here. James is right, momentum is the better one to choose here. Let's go back to, it's an open system because I'm not gonna bring the road into it. I'm not looking to see how the road is affected, or the earth as being a part of it. The change in momentum is equal to force times time. The fact that I gave you a time is the key here. In the other case, when at the 20 meters, momentum or energy. So at this point, should I consider momentum or energy at this point? Go ahead and say it, James. Okay, or not.
Energy.
Yes, you know why? Other than it's the other one?
Yeah, well, that's, yeah.
Okay. Because we have non-conservative work involved here. Non-conservative work is force times displacement. The fact that I gave you a displacement. That's the reason. So which one you use, which one's most convenient, sometimes it's a matter of what am I given. I'm given time, I'm probably gonna be thinking momentum. I'm given a displacement, probably gonna be using energy. Given a collision, I'm gonna be using both, but we're not there yet. All right, so the car is cruising along. I'm going to be concerned about momentum here, so I need to figure out what is my momentum at this point. So I'm going to call this point A, time point B, point C, and point D. Because why not? Pick your own favorite four letters. So the momentum at point A, just before slamming on the brakes. How would you find the momentum?
It's gonna be the mass of the car times its velocity.
Yes, which is 30 times 1,000. I'll do that one in my head. 30,000 Descartes, since I have it defined. While he is skidding to a stop, I know that he is going to lose momentum. So I just need to figure out what is the force acting on him. What is causing the car to slow down anyway?
The brakes. Slamming on the brakes.
What is the force?
Friction.
Yes. And I made convenient numbers. I made G 10 meters per second squared, just because it make the math simpler. If we did the force diagram here, I have weight acting down, I have friction acting back, I have normal force acting up. That's the force diagram. Oh. When I wrote down P is equal to 30,000 Descartes, what assumption did I make?
That, oh, never mind, I see the parts up here now.
Oh, yeah, no, it's defined. I guess in that case, you're assuming that I didn't lie when I wrote that.
The direction. Positive.
Yep, I assumed this way was positive. So friction is acting in a negative direction. This is gonna be equal to UK times the normal force, which in this case would be 9,000 newtons. To the left. So my impulse is force times time, so it's negative 9,000 times 2.5 seconds. Negative 9,000 times 2.5 seconds. $22,500? No. Yes.
Negative 22,000 pounds, yeah.
Okay. So it starts out with 30,000 Descartes of momentum, and then it loses 22,500 Descartes of momentum. So how much momentum does it have when it gets to when the foot comes off the brake?
$7,500. Descartes.
Thank you. All right. So that's how much momentum the car has. How fast is it going? Or how would I find it? All right, what's the formula for momentum?
Mass times velocity.
So that's equal to, so that's 7,500 Descartes is equal to the mass of the vehicle times the velocity of the vehicle at point B. And what's the mass of the vehicle?
1,000 kilograms.
And so therefore, the velocity at this point is
Is that a D or an O at the end?
that's a D.
Okay.
Would you get Amy?
I got 7.5.
The velocity is 7.5 what?
Meters per second. Would it be meters per second?
It would be. Because we divided by kilograms, Descartes over kilograms, and a Descartes, that just the kilogram would disappear when you divide by kilograms, then you're left with meters per second. All right, so we now know the car is slowed down significantly to 7.5 meters per second. That's how fast the car is going at this point, when it starts to skid 20 meters, or not, depends on if it stops or not. I have non-conservative work going on here. We can go through the formality of it. Non-conservative work is equal to the change in energy, negative non-conservative force times displacement is equal to E final minus E initial. I know my force is 9,000. Oh yeah. Actually, that minus sign really should not be there. It should be there. I anticipated the negative and I threw it in too soon. Times 20. Because the friction is opposing the motion, it's harming it, I better end up with a negative work. And that's going to be equal to my change in energy, which is K final plus U final minus K initial minus U initial. Well, the only conservative force here is the weight. And fortunately, this problem takes place on a level surface, so we'll just make h is equal to 0 there. Those are gonna go away. So we have k final minus k initial. So 1/2 times the mass times the speed squared minus 1/2 times the mass times the initial speed squared, or sorry, did that backwards, times final speed squared, and this is 7.5 squared. So it starts out with a certain amount of energy, it loses some, and then it has some at the end. Yeah, earth-shattering concept. You start with a certain amount, you lose some, you end up with a different amount. The first one I can do, in theory, 180,000 joules of energy. The second one, that's 500 times VF squared, minus whatever that is. About 25,000. $28,125
Same.
units of joules. And so we end up with, let's see, add that to both sides, so I've got negative 158,750 is equal to 500 times VF squared divided by 500. VF squared equals something, and so VF